Hello everyone, my name is Amir Mazaheri and I am here today to present our CPR 2019 work named Pay Attention, Robustifying a Deep Visuomotor Policy Through Task-Focused Visual Attention. This work has been done as a collaboration with Puya, Dr. Shah and Dr. Boloni. So let's first define our problem. So our inputs include a textual user comment like push the white plate from left to right, and a video stream that is continuously capturing the robot doing the task for us. And our job is to predict the next state of the robot, again, continuously after each frame. So basically, we want to control the robot, right? So what is a visual motor? What does a traditional visual motor structure look like? So assume that we have a robot and we have an RGB camera which is continuously capturing the visual world for us. We call the visual observation O here. We have a visual encoder that encodes the frames for us and produce the primary latent variable named Z. So primary latent variable is a representation of our visual world. Then a motor network can take the variable Z and predicts the next state of the robot as a set of joint angles or a vector of joint angles. And then we move the robot using A, update the states, and we capture the next frame, and we keep doing this cycle till we finish doing the task. But what happens if disturbance occurs? Disturbance can be physical, which means that somebody can touch the robot or touch the object while the robot is manipulating that. Or it can be visual. Somebody just throws something into the visual field of the robot. What happens? So our main goal in this paper is to design a visual motor policy which be robust against a variety of disturbances. So as you can see in this example, most of the policies fail during disturbance. Like in this case, when my friend brings his hand into the visual field of the robot starts moving like a crazy person because it goes to a state that hasn't seen it before, right? And we want to solve that. So there are many challenges with disturbance. First of all, disturbances can be visual or physical. And it is impractical to record a data set with all physical and visual disturbances because there is unlimited number of possibilities, right? So it always causes unseen visual states, and it is very hard for the robot to recover after seeing a disturbance. Once it goes to an unseen state, it starts moving like a crazy person. So our proposed visual motor structure is almost the same as traditional ones. We have a robot, we have a camera, and we have the visual observation. But we assume that we have a user which gives us a task spec G. In our case, the user gives a task as a natural language sentence. A very simple sentence like push the box. Then we show that we can design a visual network that can encode both of the text and the frame together in a way that it be able to ignore whatever is not related to the task that we want to do, and it attends to the important regions of the frames and encodes like that. So in this case, our primary latent variable Z is again output of a function named E, but the inputs to the function of E has two inputs, the observation O and the task spec G. And again, the motor network takes the Z, moves the robot, and we show that such a case is resistance against disturbance. So task-focused visual attention makes the perception of the visual world dependent to the task. So basically, Z is the output of encoding O and G, where O is the input frame and G is the textual comment. And we show that this is robust to visual disturbance. And it basically works as ignoring the disturbance and attend just the important regions which are related to the task being done. So here is the block diagram of our network. So we have these inputs, the text and the frame. So we have an encoder module which produces a latent variable Z, and we have a motor network which takes the latent variable Z and moves the robot. And we have a generator, again, which takes a latent variable Z and generates two frames for us. One is the masked frame, and one is the actual RGB frame. So it tries to reconstruct the RGB frame as well. And we have another module which we call it attention network or teacher attention network, which again takes receives the text and the frame, and it produced a masked frame for us. So basically, generator tries to mimic the teacher. That's the point of this project. And finally, we have a discriminator, which tries to distinguish between the real inputs and the fake inputs. Fake inputs are the ones coming from the generator. So let's start with the teacher network. So our teacher network job is to compute an attention on the frames based on the input sentence. It selects a few regions of the input frame given the input sentence, and we call it visual attention. So as you can see in this example, we have a text, we have a frame. It selects a few regions of the frame, and we call it the attention. And we train the teacher network separately. So input text and RGB frame are the input to the teacher network. We use a VGG19 pre-trained network to encode the RGB frame, and also we use word2vec and an LSTM to encode the text. Then we combine the encoded text with all the H by W regions of the frame, and we assign one score to each of these regions. Then a special feature pooling pulls the features from the output of the VGG19 given these scores. And finally, given the pooled feature, we try to reconstruct the text, which means that we have a multi-label classifier which says which words exist in the original input text. So we have a classification loss here to train this network. So these are some more examples. So if the textual input command is pick up blue ring, and this is the RGB frame, the masked version or the masked frame with the attention is shown here. And these are the words that the teacher network could retrieve. These are the top 4 words that the teacher network could retrieve, like in this case a ring, pick up, push, and blue. And it's another example. So now let's talk about our encoder. So the input to the encoder is a RGB image and the encoded text. Then it has 8 layers of convolutions. We also make the encoded text a spatial feature by passing it through a fully connected layer and then reshaping it. And we concatenate it with the visual features in the middle of the network. And finally, we get the output of the convolutional network, and using a reshape and fully connected, we compute a distribution for Z. So we show a distribution using the mu and sigma. And finally, by a sampling from that distribution, we sample 1Z. Then we have a generator. Generator takes the primary latent variable Z as its input. It has a fully connected and reshape layer to make the Z a spatial feature. And then we have 9 layers of deconvolutions, and finally we get a generated mask and RGB frame, and we call them the fake examples. And finally, we have a discriminator. Discriminator takes the masked and RGB frames. It has 7 layers of convolution, and finally it tries to classify the object in the frame and the color in the frame, or says it's a fake class. So let's look at the loss to train our generator and discriminator. So for the discriminator loss, discriminator tries to assign the correct class to each of the real data samples, correct shape and correct color. For the fake classes, it tries to assign the fake class to each of them. And for any random noise vector, drawn from normal distribution 0 and 1, it tries to assign fake class to it as well. So it's a technique to make the discriminator works better or stabilize the discriminator. For the generator loss, generator tries to fool the discriminator, so it generates some sample and it fools the discriminator to give the shape and color class that generator wants. And also it minimizes the feature distance between the real frames and the generated frames. We get the features from a middle layer of the discriminator. It tries to minimize the distance between, minimize the KL divergence between the primary latent variable z and the normal distribution of 0 and 1. And finally, it tries to minimize the reconstruction loss for the RGB frame and the mask frame by attention. And at the end, we have a motor network. Motor network takes a latent variable z. It has 3 LSTMs stacked, and we use escape connections to make the training easier. The motor network produces a mixture of Gaussians for us. So we have a vector named alpha, which are the Gaussian coefficients, mu, which are the Gaussian means, and sigma, which are the Gaussian standard deviations. And we do a sampling from this mixture of Gaussians, and we call it next state prediction, or the joint angles. So the loss for the motor network is a negative log likelihood as MDN, or mixture density network, which takes a ground truth joint and sees how well it fits in this mixture of Gaussians. And N of G is a number of Gaussians that we use. So experimental setup. First, we record some demonstrations using a game controller and a robot. We record this. We save all the joint angles. We train the network that I described earlier. And finally, we test it on the robot. So we let the robot to, given a sentence, like here this sentence is pick up the blue ring, we let the robot to run it for itself. And a human judge observe it and decide if the robot was successful or not doing this task. So let's look at some qualitative results. As I mentioned before, most of the times, methods without task-focused attention, most of the methods fail. For example, in this example, the sentences push their red box from left to right. And as you can see, the robot cannot do anything. But in the almost same scenario, same object, the same way of the disturbance, we see that with the task-focused attention, it can easily move the object and come back to the beginning point. In the middle box, I show the generated attention of the robot. So it's another example again. Here my friend disturbs the robot multiple times. So without task-focused attention, it fails. But with the task-focused attention, even though my friend disturbed the robot multiple times, each time robot can retrieve and come back and pick up the object again. So these are some quantitative results. So first I show the sentences. So these are all the sentences starting with the pickup. So pick up Red Bull, pick up the white towel, pick up blue ring. And first we show the results in the benign condition where we don't have any disturbance. If we use just the encoder to train the whole network, the results for the average results for the pickup sentence is going to be 15%. If we use a traditional VAE, which means we don't have discriminator, it's just a variational autoencoder, the results can be 40%. If we use the VAE with discriminator, which is a VAE again, but without the task-focused attention, the results going to be 43%. But when we use our proposed task-focused attention, even in benign condition, we can show that the results boost. Then in the environment with disturbance, we can show that our approach can boost the results a lot, like from 3.3% to 58%, is a huge improvement. Again, the same for the sentences for the push some object from left to right. Again, here I show some sentences. As you can see, again, you see the same trend here. In the disturbance environment, from 7.5% to 55%. And this is the average over all 12 sentences. Thank you very much. Please contact us if you have any questions.
Okay, great.